Hello, welcome to this lecture, which is going to be about the materials that go into manufacturing and formation of magnetic materials within within cars and automotive applications. So in this lecture, which is the third part of my lectures on materials for automotive sector, we will be looking at electromagnetism and the importance of the electric motors in cars. We'll look at what are the different groups of materials that are in this specific area, how magnetic properties develop within the materials, and then we will be looking at, finally, the sustainability issues and the availability of the material issues and challenges that we've got in this sector. So as we've covered before, there are so many different sensors and moving parts within the car. And a lot of these movements and a lot of these sensing come from or originate from a specific properties that are within, generally speaking, ceramic materials. So if you look at just electric motors, which they convert electricity into kinetic energy, and that is a crucial part that happens within cars, is, in generally speaking, we've got almost half of the electricity that is used to power electric motors. But if you look at global consumption of electricity, about 30% just used to power electric motors. Now there are quite a lot of these parts within cars. If you move it beyond industrial motors, if you look at the electric motors that exist in a modern car, we've got so many of these smaller motors that will activate movements within cars. So about 36 kilograms of these motors exist in a typical car. Now this is not a new idea. It's been electric cars and electric generation of the kinetic energy using electricity has been in the automotive sector for so many years. In fact, the original ideas of cars, or before 1912, the majority of cars were basically starting using a crank. So you had to actually initiate that kinetic movement within the car to do the explosion of the fuel inside the cylinders, and as a result of that, starting the car. But then in 1912, Charles Kettering came up with the idea of using electric motors, electric starters, to get rid of cranks and to start the cars much easier. So the car with no crank was a Cadillac in 1912. Now the whole concept of this comes from the concept of electromagnetism, which talks about the interaction of electric field and magnetic field, and how the movement of charge could happen as a result of this interaction. So this was first discovered by Michael Faraday. And basically the concept is, if you've got a conductor within, if you put a closed loop of conductor inside a magnetic field, the charges will start to move. Now these movement of charges, if we reverse the direction of the magnetic field, then it could be reversed, the direction of movement could be reversed. As a result of this movement of charges and the changes in direction, if we design a setup that we've got a wire that is rotating, and we put magnetic cores or magnetic parts around that, what we will see starting kinetic movement of parts within the device. So there is an interesting video, that I've put the link in here. This is fairly old, so when you look at it, the concept of modern is quite different to what we call modern now. But that explains how electromagnetism and how electric motors work very well, and how people moved from cranks to electric motors to start the cars. Okay, how this changes in the magnetic properties of materials happens, and what they are usually made out of. So a lot of magnetic materials that are used in electric motors are made out of ceramic materials, generally speaking from ferrites. Now ferrite is a general terminology that are given to these these groups of materials, because the best known magnetic material to us has been a magnetite, which is an oxide of iron or a ferrite. So generally speaking, there are two different types of magnets, which, depending on how well they interact with the applied magnetic field, or how easy it is for them to get magnetized, or how easy for them is to lose their magnetic behavior, we divide them into two different parts. So the first one would be a soft magnetic material. That means you can easily magnetize it and you can easily demagnetize it. So what you can use them for is in applications such as memory cores and so on, because you can, by applying a signal, you can easily create a new position within the material, a new magnetic property within the material. So you can erase that afterwards as well if you needed to, because it's a soft magnetic material. Hard magnetic material is, and the opposite, is a material that will be very difficult to magnetize, but once it has been magnetized, it will not lose its magnetic property very easily. So that is the one that is used in a lot of magnetic latches and motors and so on. Now I explained to you how this happens using this graph, which basically is a typical magnetization graph for a specific type of material. Now we've got in this graph, we've got the magnetic field. That is basically, this is the application of the magnetic field, so that is increasing. That's where we've got the amount of magnetization. So B is our magnetization. Okay, so what happens within material? We've got regions within the material which we call as domains. So domains. And these are small regions within the structure of material where if we consider something like this as a material, then we can show these domains and the strength of their magnetic behavior by arrows. For example, we've got random domains which are in the form of we are inside the material, different direction of their magnetic field. Now, once we start to apply a magnetic field, what is going to happen if we go along that direction? So we start to apply the magnetic field, so this is start to increase. What you'll see is that the magnetic behavior within the material starts to form, and we will get to a point where all these domains within the structure of the material are in the same direction, so they have been magnetized, all of them in the same direction, and the total magnetization that you have in the material is the result of all these domains to move towards one direction. So that is what we call as the saturation point, or saturation magnetization. Now the interesting thing is, if you start to reverse the applied magnetic field, what is going to happen at that point is that if we take the same, if we say this is the same one, what is going to happen out of those 7 domains, 6, for example, will stay in the same direction, or 4, 5 will stay in the same direction, and 2 of them will reverse. So what will happen is that you will get something we call as a remnant polarization, or we show it with R. That is what is remaining within magnetization, which is remained as a result of the applied magnetic field to become 0. So that's the point, that we've got 0 magnetic field. So some of that magnetization starts to be preserved within the material. Now, if we apply the same amount of, so if that is H1, and if we apply the same amount of H1, or sometimes maybe even higher, if we get to the H2 points in here, what is going to happen in here in terms of domains is that you will see that still we might have domains which are in one direction. Let me just erase that again, it's not doing its job well. So we'll have some domains along that direction within the material and some domains in the opposite. So the total balance will become zero. We'll have some parts which are one direction magnetized, the other ones which are the other direction magnetized. So the accumulation of them will give you total zero magnetization. And what we'll see at this point is the opposite situation for your saturation of the magnetic field. So all of these are now in the opposite direction. This is not working really well. So what we'll have changes within the locality of materials, where we call them as domains, where these are small points or small regions within the material that can get magnetized. And then if we start to apply the magnetic field, then we can arrange and reorient all of these, the smaller domains, into one direction, and we get total magnetization or saturation magnetization within the material. Now if we start to reverse that, we'll start to see that some of those will maintain their magnetization, some of them will go smaller. So usually what we'll have a situation where our remnant polarization is usually smaller than our saturation polarization. Now what you see here, so this is the amount of, as you can see here, the amount of field or magnetic field that we require to completely remove the magnetization within the material is called coercive field. So that's Hc. I'll write it again. Hopefully this time it will keep C. So Hc, that is our coercive field. So that's the amount of energy that is required to get to that position, to completely remove the magnetization within the material. Now the shape of this graph is quite important. As I said, if you've got a square type shape like this, you've got a hard magnet, so that it is difficult to magnetize it to get to that point. But at the same time, if you remove the magnetic field, you still maintain your magnetization. Or if you've got a narrow magnet, a narrow shape like this, that means it is very easy to magnetize it, but at the same time it's easy to demagnetize it as well. So this will become a soft magnet, as the larger one become a hard magnet. Right, so there are different groups of magnetic ceramics. As I said, they are generally referred to as ferrites, and I've given you some examples in terms of what could be a typical structure for a soft magnet and what could be a typical structure for a hard magnet. Now there is another group as well, which they include a lot of these rare earth ferrites. So these are the ones which are quite an interesting one, because a rare earth, as it can come from it, from the wood, is not that much available to us. So it is quite important, and we understand that if we are working towards much better magnets, we are typically using much more of these rare earth ferrites. That means we've got more difficulty in terms of availability and sustainability of these materials. Now, electric vehicles are getting more and more common. By 2030, apparently, there won't be any new cars which are not electrically driven. And electric vehicles, they have a lot of electromagnetic devices in them, so more than about 100. That means that if we are to look at moving away from internal combustion engine, relying more and more on these electric vehicles, we have to think about what sort of material systems we are using. Because a lot of these materials, as you can see here, we've got materials which are not easily available to us. So these rare earth elements could become quite important in the next generation of electric cars because they are massively used within the structure of either batteries or magnets that are used either in the sensors or in the electric vehicles. As you can see here on this graph, we've got more or less about 20% of rare earth elements that are being made manually, are being consumed in magnets. The same as about 10%, as you can see in the battery alloy market. So this is heavily relying on older generation of batteries. So that would have been nickel metal hydride. So that would have a lot of these rare earth elements in them. So lithium, newer versions of batteries, lithium-ion batteries, will have a smaller amount of material. At the same time, as we will be discussing about battery materials later on, you'll see that this is still an issue. Sustainability and availability of resources to us is quite an important aspect in this industry. So we covered the fact that how important electromagnetic devices are. We looked at what sort of typical compositions are for applications in magnetic materials within electric cars. At the same time, I introduced you to the concept of sustainability and resource availability, especially with the fact that there are elements within these devices, within the magnets, as we will see later on, within batteries that are heavily depleted in the earth crust and are not available to us. It's one of the reasons the cost will go up. Well, and it is another reason that we should be looking at developing alternative systems, alternative material systems that will allow us to function the same way that we used to do for electric devices and batteries and so on for the next generation of cars that will come to the market. Thank you very much.